Hello all, welcome to Unacademy. Today we will going to see our next lecture on discrete mathematics, that is lecture number 9. In the previous set lecture we have seen different topics on discrete mathematics. In this lecture we will see the countable sets and discrete numeric function. Okay, mean by countable sets and discrete numeric function, that part we will see in this lecture. No. Before going to start this, let me introduce myself. Myself, Dhanashree Mam. I completed my MSc in Mathematics from Mumbai University and also having 13 plus years of teaching experience. I mentored more than 10,000 plus students for the engineering. I'm just giving review of how to install the Unacademy's learning app. First, go to your mobile's Play Store app and then search Unacademy's learning app. After that, install the Unacademy's learning app. Then Step 3, here you have to manage your goal. जैसे कि हम लोग यहाँ पे अभी GATE and ESE के लिए पढ़ रहे हैं, so you can manage your goal here GATE and ESE, and then after that you can take any subscription plan, either for plus subscription, free courses, special classes, that is up to you for which course you want to study. But अलग हर एक plan के अलग अलग benefits है. जैसे कि आप लोग plus subscription ले रहे हो तो you will get a one-to-one face-to-face educator that you can solve your each and every doubts. Okay. Then next is press the get and ESE button, get subscription button, so that you will get the subscription of the your subscription plan. And then next, here you can choose the subscription plan either for 12 months, 6 months, 24 months, it is up to you. But if I'm going to suggest you, if you are going to prepare for the GATE 2023, then definitely you will take a subscription plan of 24 months, so that it will be more easy and very convenient to do your study within this plan. And the most important thing I'm going to tell you, to take the any subscription plan, free subscription to any subscription plan, and to get the 10% discount on your subscription plan, you can use my promo code, that is DSP, to get the 10% discount on your subscription plan. And the next is last thing is, here you can use any of this method. Payment method you can choose either for debit card, credit card, EMI, UPI, wallets, net banking, anyone you can choose which is suitable for you. Pay the subscription fees. Okay. And the next is, to unlock any free plan of Unacademy, you can use my promo code, that is DSP, for the special classes, live test series, quiz contest, and Unacademy Combat. Okay. Now, next we will go further. Yeah. That starts our actual topic. It is countable sets, or it is also called as denumerable set. Okay, what is the definition of countable sets? An infinite set is said to be denumerable if its elements can be put in one-to-one correspondence with the set of natural numbers. Okay? An infinite set is said to be denumerable if its elements can be put in one-to-one correspondence with the set of natural numbers. That is, there exists at least one mapping F from the set A to the set N such that F is 1, 1 and onto, then the set A is known as denumerable set. Okay. If such correspondence does not exist, then the set is known as non-denumerable set. Okay. It means, to show that any set is countable, we have to establish the 1-1 correspondence between the given set to the set of natural number. Okay. To prove that any set is countable, we have to establish a 1-1 correspondence between the set of natural number to the given set. Okay. Now, your countable set, in short, a set which is either empty or finite or denumerable is called as countable set. Any finite set is countable. Okay. Now, uncountable set. A set which is non-denumerable is called as uncountable set. It means we cannot establish any relationship between the given set to the set of natural number. That set is said to be uncountable set. Okay. Now, we'll see the examples here. Countable sets and uncountable sets. For example, 5 is a countable set, right? First example, Phi is countable set. Okay? That is cardinality of phi is equal to 0. Okay? Therefore, it is a countable set. Phi is countable set, and then set A is equal to countable. Second, suppose A is equal to given finite set A, B, C, D. This is finite set, as by the definition of a countable set of a set is which is finite. Then it is also empty set or finite set. Then it is countable set. Okay, so A is a countable. We know that the cardinality of this set A is equal to 4. Given set A is countable. Okay, the set of all integers is countable. The set of all integers is countable, because we know that we can establish the relationship. There is a one-to-one correspondence between the set of integers to the set of natural number. We can establish the relationship between set of integers to the set of natural numbers. Then the set of integer, for the set of integers is countable. Okay, therefore the given set of integers is countable. Now if you want, we can see that here a one-one correspondence between set of integers and natural number. Example, to prove that set of integers is countable, we can establish a one-one correspondence between set of integers to set of integers and natural number n. Can be made as follows. Suppose this is your set of integers 0, 1, minus 1, 2, minus 2, and so on, m minus m, right? So we can give the relationship between here set of natural number with 1, 2, 3, 4, 5, and so on, 2m, 2 into cardinality of m plus 1, and so on, right? So there is a one-to-one correspondence between set of integers to the set of natural number. One-to-one correspondence between set of integers to the set of natural number. Therefore, we can say that the set of integers are countable. It is a function from, we can define a function, it is a function from I to n, such that f of m is equal to 2m if m is positive. Okay, f of m is equal to 2m. See here, f of m is equal to 2m if m is positive. Here 1 is positive, here 1 is positive, and f of m is equal to 2 into cardinality of m plus 1 if m is negative of 0. If m is negative or 0. So here we establish the one-one correspondence between set of integers to the set of natural number. Therefore, the given set of integers is a countable. Okay. So here we can establish the relationship between set of integers to the set of natural numbers. Therefore, there is a one-one correspondence between set of integers to the set of natural number. Hence, set of integers are countable. Okay. Now, we'll take the next example. So, prove that set of rational numbers in a closed interval 0, 1. Example 2, we will see that. Prove that set of rational numbers, prove that set of rational numbers in closed interval 0, 1 is countable. Okay. Now, show that set of rational numbers in 0, 1. So we have to establish the relationship between set of rational numbers between 1 and set of natural numbers. So we have to establish the relationship between set of natural numbers network issue there is. Okay. Now here, prove that the set of rational numbers in closed interval 0, 1 is countable. To show that closed interval 0, 1 is countable, we have to prove that there exists at least one function f from closed interval 0, 1 to n such that f is 1, 1 on 2. We arrange the rational numbers of the interval according to the increasing denominators as 0, 1, 1 by 2, 1 by 3, 2 by 3, 1 by 4, 1 by 5 and so on. Okay, in this manner we will establish the 1, 1 correspondence between the rational numbers in the closed interval 0, 1 to the set of natural numbers. Okay, now see, then 1, 1 correspondence, we will write the 1, 1 correspondence. Then the 1, 1 correspondence can be indicated as 1 correspondence can be indicated as 1, so 2, 1, 3, 1 by 2, 4, 1 by 3, 5, 2 by 3, 6, 1 by 4, 7, 3 by 4, 8, 1 by 5. Hence, the set is countable. Hence, the set is countable. Okay? The set is countable because there is 1, 1 correspondence between the rational numbers in closed interval 0, 1 to the set of natural numbers. Hence, the set is the set of rational numbers in closed interval 0, 1 is countable. Okay. Now next is, we will prove that the set of real numbers in closed interval 0, 1 is not countable. So keep it in mind, set of rational numbers. So we will see this example. Prove that set of real numbers, the set of real numbers in closed interval 0, 1 is not countable. In the closed interval 0, 1 not countable. The set of rational numbers in closed interval 0, 1 is countable, but the set of real numbers in closed interval 0, 1 is not countable. Okay, so to prove that this, will any real numbers between 0 to 1, any real number between closed interval 0, 1 can be written in the following manner. In the following manner in a unique decimal form. A unique decimal form. Okay. So that is, suppose A1, A2 up to AI and so on. Where, now this is where AI is any of the digits. AI is any of the digits from 0 to 9. Right? 0, 1, 2, up to 9. Assume that, we'll assume contrary and we will get some contradiction, so that the set of rational numbers in closed interval 0, 1 are not countable. Okay, so assume that the set A of all real numbers in closed interval 0, 1 is countable, then the elements of A can be written in a sequence therefore therefore uh, done in a sequence. Therefore, we can write here A is equal to x1, x2, and so on up to xn and so on, where xi belongs to A. Okay. Now each xi belongs to A can be written in decimal form, can be written in decimal form, can be written in decimal form as we write the x1. x1 is equal to 0.A11, A12, A13 and so on. x2 is equal to 0, A21, A22, A2 and so on. x3 is equal to 0.A31, A32, A33 and so on. Okay. And so on. xn is equal to xn is equal to 0.an1, an2 and so on, an3 and so on. Okay. So this is your x1, x2, x3 and xn. Now we can write this x1, x2, x3 and so on, since all the elements of A are countable, right? All the elements of A, since all the elements of A are countable, all the elements of A are countable, we can establish one-one correspondence between the elements of A, and natural number, right? There is a one-one correspondence between 1 to 0.A11, A12 and so correspondence between 0.821, A22 and so on, C2, 0.831, A32 and so on. Now construct a decimal number. Here y equal to 0.b1, b2 and so on. b1 is equal to 0 if aii is not equal to 0, and b1 is equal to 1 if aii is equal to 0. Okay, so you will get b1 is not equal to, hence b1 is not equal to a1, b1 is not equal to a11, right? And b2 is not equal to a22, b3 is not equal to a33 and so on. We'll get bi is not equal to aii, right? For any I, and y is not equal to x1, since it's differed from first decimal place. Y is not equal to x2 since it's differed from x2 and the second decimal place, and so on. Y is not equal to xi, since it differs from xi and the ith place. Thus, the number y is equal to 0.1, b1, b2 up to bn and so on lies between 0 and 1, and it's different from each of the numbers in the above. Therefore, it is not an element of A. Okay, so which is contradiction. If it is an element of A, then definitely it must be belongs to the closed interval 0, 1. But here, which is contradicts our assumption that A is countable. Hence, A is not countable. Right? Hence, A is not countable. Are you getting it? It's a little bit different type of proofs. So we assume contradictory that A is countable. As A is countable, we can write there is a 1-1 correspondence between the numbers, real numbers between closed interval 0, 1 to the set of natural numbers. But here we are getting some number y which cannot be represented. We cannot give the representation in terms of set of natural. There is no 1-1 correspondence between set of natural number to the this real number. It is contradiction. Therefore, A is not countable. Okay. Now we'll see the properties of countable and uncountable sets. A subset of a countable set is countable. A superset of an uncountable set is uncountable. Union of countable sets is countable. That is, A and B are countable sets, then A union B is also countable. And Cartesian product of countable set is countable. That is, A and B are countable sets, then A cross B is also countable. And union of countable collection of countable set is countable. That is, union of I varying from 1 to n is countable if each AI is countable. Okay. Now one more thing is there also the some remarks. The set of real numbers in closed interval 0, 1 is an uncountable set. Hence the superset closed interval 0, 1, that is the real number set, is an uncountable set. Right? So here also we can use that same property. Since set of real numbers in closed interval 0, 1 is uncountable. Okay. Hence the superset of closed interval 0, 1 is also uncountable. Also uncountable. That is, set of real numbers is uncountable. Okay. And set of irrational numbers is also uncountable. And P of n, power set of natural number, is also uncountable. Right? Power set of n is uncountable. Are you getting it? The countable sets and uncountable sets. Okay. Now the next point, we move to the pigeonhole principle. Very interesting, a pigeonhole principle. Okay. So it automatically, in general also there is a function. Because of that, this pigeonhole principle is developed. See, suppose there are 10 pigeons. How many and there are only 7 holes. So how many ways each pigeon can occupy the 7 holes? It means at least one hole must contain more than one pigeon. Okay, there are 10 pigeons and only, yeah, there are 10 pigeons. 1, 2, 4, 5, 6, 7, and 7 holes. So how many ways one pigeon, so at least there is at least one pigeon hole must occupy more than one pigeon. Okay? There is at least one pigeon hole which occupy more than one pigeon. Yeah. So there is at least one pigeon hole which occupy more than 7 pigeons can be seated like this, and remaining 3, so must one of that can be occupied this, or one hole must be occupied at least one pigeon, more than one pigeon. Okay? 2 or more pigeons. Let A and B be finite sets. See here, pigeonhole principle says that if there are many pigeons and few pigeonholes, then there must be some pigeonholes occupied by 2 or more pigeons. Let A and B any finite sets and cardinality of A is greater than cardinality of B, then for any function f from A to B, there exists A1 and A2 belongs to A, such that f of A1 is equal to f of A2. Okay. such that f of a1 is equal to f of a2. So this is your pigeonhole principle. Now the suppose, for example, also we can see there are 11 shoes are selected from 10 pairs of shoes. There must be a pair of matched shoes among the selections. Okay, and here 11 shoes are the pigeons and 10 pairs are the pigeonholes. The pigeonhole principle also known as shoebox argument. Okay, pigeonhole principle is also known as shoebox argument. Now we'll see the extended pigeonhole principle. Okay, if it is in multiple 3 times, if there are m pigeonholes and more than 3m pigeons, then the 4 or more pigeons will occupy at least one of the pigeonhole. In general, if the number of pigeons is much larger than the number of pigeonholes, then pigeonhole principle can be extended as, see, if n pigeons are assigned to m pigeonholes, then one of the pigeonholes must be occupied by at least n minus 1 by m, integral part of n minus 1 by m plus 1 pigeon. So here we can write the remark. So n minus 1 by m is a integer division of n minus 1 by m. For example, 10 by integral part of 10 by 3 is 3. We cannot write here 3 point or something. We will take only the integral part of that. 16 by 3. So integral part is 5. 9 by 2. Integral part is 4. Okay. So we will take this. Now see here. Show that there are 30 people. Right? Show that there are 30 people are selected, then at least 5 people must have been born on the same day of the week. Now, if you observe here, the number of peoples are much more than the number of days, right? So, how many number of days here? Number of peoples are, we can, so here we will use the extended pigeonhole principle. By extended pigeonhole principle, can write here n is equal to 30 and m is equal to 7. Whole it means the number of days. Okay. Here n is equal to 30 and m is equal to 7. Now, so at least there are at least integral part of n minus 1 by m. It means 30 minus 1 by 7. Right. So 30 minus 1 by 7, it means 29 by 7. Right. So, and plus 1 equal to plus 1. So 29 by 7, the integral part is 4 and plus 1, that is 5. Hence there are at least 5 people must have been born on the same day of the week, very simple, with the help of pigeonhole principle. Okay, next is show that 7 colors are used to paint 50 bicycles. At least 8 bicycles will be of the same color. Easily you can show that here by extended pigeonhole principle. By extended pigeonhole principle, we have here n is equal to 50, m is equal to 7. So 7 is less than 50. So we can write here n minus 1 by m plus 1. N minus 1, 50 minus 1 by 7 plus 1. 50 minus 1, 49. 49 by 7, integral part of this. The integral part of 49 by 7 is 7 plus 1, that is 8. Hence, There are 8 bicycle will be at least 8 bicycle will be of the same color. At least 8 bicycles be of the same color. Of the same color. Right? This next point is third point is your discrete numeric function. Okay, a function if from natural number set with 0 to a real number set R is known as a discrete numeric function or numeric function if x is defined from set of natural number to the set of real numbers. Okay. If x is defined from set of natural number to the set of real numbers is a discrete numeric function. Then x0, x1, x2, x3 up to xk denote the values of numeric function. The numeric function is also known as a sequence. Okay. The numeric function is also known as the sequence. Now see, for example, here and see the example. For example, here xk is equal to, we define 2 raised to k. Take this example in the next page. Here 2 raised to k and k, if k and this, when 0 is less than or equal to k, less than 6, and this is when k greater than or equal to 7, right? So this discrete numeric function can be written as discrete numeric function can be written as okay. So here x is equal to your, now for 0 to 6, so x is equal to 0, sorry, k is equal to 0, so 2 raised to 0 is 1, so 1, k is equal to 1, 2, k is equal to 2, 4, k is equal to 3, 8, k is equal to 4, 16, k is equal to 5, 32, k is equal to 6, because here is no less than or equal to, only less than 6, so up to 5. Now k greater than or equal to 7 is k, so here 7, 8, 9, 10 and so on. This is your discrete numeric function for the given sequence x. Here it's a very simple point, discrete numeric function, right? So this discrete numeric function can, suppose x is given, then you can write the sequence also. Okay. For example, basic, now we will give the basic operations on numeric function. Okay. Basic operations on numeric function. Very simple. Suppose let x and y be two numeric functions. Let x and y be two numeric function. Then z is equal to x plus y is the addition of two numeric function. The addition of two numeric function where zk is equal to xk plus yk. Okay, so addition of these two numeric function is xk plus yk, right? Similarly, we can take the multiplication of x and y, multiplication of x and y, the numeric function, say d, then d is equal to x into y, where dk is equal to xkyk, where dk is equal to xkyk. Okay. Now next is scaling. Third operation is scaling. If a is a number, then a into x is a numeric function, then a into x is a numeric function, and a is known as scaling factor. Then linearity, fourth one. Linearity. If a and b are real numbers, then t is equal to ax plus by is a numeric function where tk is equal to axk plus byk, right? So this is your linearity function. So for example, if you take, suppose xk is equal to 1 by 3k, right? And 5x is equal to, so 5 scaling factor addition of these two numeric function you can take easily. Okay. Now next is generating function. In by generating function, here now to introduce another way to represent the numeric function. For the numeric function x is equal to x0 x1 up to xk, we define an infinite series x0 plus x1z plus x2z square plus x3z cube plus and so on plus xkz raised to k plus and so on, which is known as generating function of the numeric functions x, and it is denoted by a of z, where a of z is equal to x0 plus x1z plus x2z square plus x3z cube plus and so on xkz raised to k plus and so on, which is also be written as summation k varying from 0 to infinity xk into z raised to k. This is your generating function. And in this generating function, see, suppose your discrete numeric function can be written in this form of 1 by 2 raised to 0, 1 by 2 raised to 1, 1 by 2 raised to 2, and so on, 1 by 2 raised to k. Then the same discrete numeric function can be written in the generating form a of z is equal to, here we can write 1 plus 1 by 2z plus 1 by 2z bracket square plus 1 by 2z bracket cube plus and so on 1 by 2z bracket raised to k and so on, which is an infinite geometric progression with first term 1 and common ratio is an infinite geometric progression with first term 1 with first term 1 and common ratio and common ratio 1 by 2z, right? That is a is equal to 1 and r is equal to 1 by 2. So hence a of z we can write here a upon 1 minus r, so which is equal to 1 upon 1 minus 1 by 2 is equal to 2 by 2 minus z, okay? Where 1 by 2z is less than 1, r is less than 1. The generating function a of z is equal to 2 upon 2 minus z for the given discrete numeric function. Now, an example here, find the discrete numeric function corresponding to the following generating function. Now here generating function is given, we have to find out the discrete numeric function. Here conversely we have given that here discrete numeric function, then find out the generating function by using this. Okay. Now here generating function is given, we have to find out the discrete numeric function. means here 1 upon 5 minus 6z plus z square. So how we can factorize this? 1 upon 5 minus 6z plus z square. So can I write in a factor form 5 minus z into 6 minus 1 minus z? Factorize it. 5 into minus 5z minus z minus 6z and minus minus plus z square. Right? So this is your factors. Now we know that here 1 upon, so by using partial fractions we can find out the solution for this. Now see, 1 upon x minus b. So how we can write 1 upon x minus a into x minus b is equal to 1 upon here a minus x. You can write here opposite way. 1 upon a minus x into b minus x is equal to, we can write 1 upon a minus b to bracket 1 upon b minus x minus 1 upon a minus x. So exactly similar way. This is your a, this is your b, a minus x, b minus x. You get 1 upon a minus b. So 5 minus 1, that is 4. Upon 1 minus z, b minus x, 1 minus z, minus 1 upon 5 minus z. So very simple way by using partial fraction. Okay. So 1 upon 4 as it is. Now 1 upon 1 minus z. Can I write this as 1 upon 1 minus z as 1 minus z bracket raised to minus 1 and minus 1 upon 5 into bracket 1 minus z by 5. Right? So ultimately here is 1 by 4 into 1 minus z bracket raised to minus 1 minus 1 by 5 to 1 minus z by 5 bracket raised to minus 1. Yeah? Here we can write 1 by 4 to bracket 1 minus z bracket raised to minus 1. So we can use the binomial expansion as if there is minus sign, so all are positive. 1 plus z square plus z cube plus and so on. Minus 1 by 5 as it is. And here is 1 minus z by 5. So we can write 1 plus z by 5 plus z by 5 bracket square plus z by 5 bracket cube plus and so on. Right? So here 1 by 4 common to all. So you can write this in the summation form, summation k varying from 0 to infinity 1 raised to k into z raised to k minus 1 by 5 is constant and summation k varying from 0 to infinity 1 upon 5 raised to k into z raised to k. Right? We required only discrete numeric function. It means we required only the coefficient of z raised to k. Right? So we can write here 1 by 4 into 1 raised to k minus 1 by 20. 1 by 4 into 1 by 5. 1 by 20 into 1 by 5 raised to k, where k is greater than or equal to 0. This is your discrete numeric function xk. Yeah. So with the help of this, you can find out the generating function the similar way. I hope it is clear to you how to find out the discrete numeric function with the help of this generating function. Okay. Now again we will solve the next one. Find the discrete numeric function for the following generating function. A of z is equal to 7z square upon 1 minus 2z into 1 plus 3z. Okay. Get here A of z is equal to minus 7 by 6 plus 7 by 6 into z plus 1 upon 1 minus 2z into 1 plus 3. 7z square, finding A and B. We'll get this. So A of z is equal to here B of z plus C of z. Here A of z is equal to C of z is equal to 7 by 6 z plus 1 upon 1 minus 2z into 1 plus 3z, right? So we will solve this 1 minus 2z into 1 plus 3z. Okay, so you can calculate this value of a and b and then find out the generating function. Okay, so here you will get z plus 1 upon z plus 1 upon 1 minus 2z to 1 plus 3z is equal to a upon 1 minus 2z plus b upon 1 plus 3, right? Put here a into brackets, we'll get z plus 1 is equal to a into 1 plus 3z plus b into 1 minus 2z, right? Get z plus 1 is equal to, now put z is equal to here minus 1 by 3, z is equal to minus 1 by 3, minus 1 by 3 plus 1 is equal to, it will become 0, and minus 1 by 3 minus minus plus 1 plus 2 by 3, 1 plus 2 by 3, it means plus 2, 5 by 3, 5 by 3b, right? Minus 1 by 3 plus 1, 3 minus 1 by 3, so 2 by 3, right? So 2 by 3 is equal to 5 by 3b, so which implies b is equal to, here b is equal to 2 by 3 upon 5 by 3 multiplied by 3 by 5 is equal to 2 by 5, equal to 2 by 5. Now put b is equal, z is equal to 1 by 2. Put here only. Put z is equal to 1 by 2. 1 by 2 plus 1 is equal to 1 by 2. So 1 plus 3 by 2. 2 plus, so 5 by 2a. Right? Here is 0. Here 1 by 2 plus 1. 3 by 2 is equal to 5 by 2a. 3 by 2 is equal to 5 by 2a. Guys, a is equal to 3 by 5. Just put the values. A is equal to 3 by 5 and b is equal to 2 by 5. 7 by 6 as it is. Right? Of z you will get z plus 1 upon 1 minus 2z to 1 plus 3z is equal to, get 3 by 5 into 1 upon 1 minus 2z plus 2 by 5 into 1 upon 1 plus, right? By 5. Okay. And into 7 by 6. So ultimately C of z is equal to what? 7 by 6 into this. 3 by 5 into bracket 1 minus z bracket raised to minus plus and plus 2 by 5 1 plus 3z bracket raised to minus. Now expand by 5 into bracket 1 plus 2z plus z square plus 2z cube plus and so plus 2 by 5 into bracket 1 minus 3z plus 3z square minus 3z cube plus and so on, right? Ultimately here get 3 by 5 into only z plus 1 upon 1 minus 2z to 1 plus 3, right? So here you will get 1 plus 2z 1 plus 3, so 1 summation here 3 by 5 get summation k varying from 0 to infinity, that is 2 raised to k to z raised to k, right? Plus 2 by 5 into summation k varying from infinity into minus 3 raised to k, minus 3 raised to k into z raised to k, right? And whole multiplied by C of z is equal to 8 7 by 6 bracket 3 by 5 summation k varying from 0 to infinity 2 raised to k to z raised to k plus 2 by 5 into summation k varying from 0 to minus 3 raised to z raised to k, right? So multiplying you get 1 by 30 2 raised to k plus 14 into 30 to minus 3 raised to k. Okay, that's C of z. And total your A of z is equal to C of z plus C of z, right? But B of z is nothing but only 1 raised to 7 by 6. 7 by 6 plus 21 upon 30 raised to k plus 14 upon 30 plus 3 raised to k is here numeric function xk. You are getting it clearly, where k is greater than or equal to 0. Yeah, greater than or equal to 0. It's a very simple to find out the discrete numeric function. So also see one more example we can see. Next third function. Find the numeric function for the numeric function for A of z is equal to 2 upon 1 minus 4z square, right? You can write A of z as 2 upon 1 minus 4z square, so 1 minus 2z into 1 plus 2, right? That A of z is equal to 1 upon 1 minus 2z plus 1 upon 1 plus 1, 2 get cancelled out, 1 upon 1 plus 2, Okay, 1 upon a plus b minus b. Right here, 1 upon 1 plus 2z, 1 upon 1 2z. Okay, nothing, 1 minus 2z bracket raised to minus 1 plus 1 plus 2z bracket raised to minus 1. As it is plus minus sign, so all are positive. So a of z is equal to 1 plus 2z plus 2z square plus 2z cube plus and so on plus 1 minus 2z plus 2z square minus 2z cube plus and so on. Okay? Nothing but summation r varying from infinity 2 raised to r into z raised to r plus summation r varying from 0 to infinity minus 2 raised to r into z raised to, right? Get xk or ar discrete function, then ar is equal to 2 raised to r plus minus 2 raised to r where r is greater than or equal to 0. Okay? That's it. Your discrete numeric function. Okay. Now today we cover almost all the topics here: countable sets, uncountable sets, then pigeonhole principle, and generating function, and discrete numeric function. Okay. When the generating function is given, how to find out the discrete numeric function, and when the discrete numeric function is given, how to find out the generating function. Okay. So I hope it is clear to you each and every concept here. See, from Monday, I will be here for the Unacademy's new channel, that is semester exam channel. I will be there available from Monday from the same time 11:50. Okay? If you are liking my videos, please do like, share, and subscribe. Thank you so much.